Oh boy, that's a little bright there. Get that fixed up a little bit. Either way, always trying to get the lighting going here. Okay, welcome to week 3. This is, of course, the ingredients of life. This is to me one of my most favorite subjects to talk about. Whenever I'm in class, talking about the ingredients of life is just amazing. And interestingly, if you pull up the chapter that I have on this in the cover, I have a picture of a Hubble image of galaxies called the Ultra Deep Field View. And you're probably going, "Oh no, here goes Dr. Kennedy again, another astronomy lesson in biology." But when we talk about the ingredients of life, it really makes sense because it's in this chapter that you really start to learn like our connection to the universe. It's astounding. So I love that image of the Hubble Deep Field View because in a very tiny part of the of our night sky, there are tens of thousands of galaxies, and I always think of all the biology out there amongst those galaxies and all those grains of sand. Sorry, all the stars. And like the stars was a reference to like there's more stars in the universe than there are grains of sand on all the beaches in the world. So lots of room out there for biology. But let me get back to some of the biology and the ingredients of life. And what do you need for life? What do you need to have a living system? You need energy, right? And of course, you need building blocks. You need elements like carbon, nitrogen, oxygen, and hydrogen. Those 4 elements, hydrogen, carbon, nitrogen, oxygen, that is 96% of you are these elements. And yet these elements, of course, are made up of these subatomic particles called protons, neutrons, and electrons. And here's our connection to the universe, right? Our universe is about 13.8 billion years old. It's really old. But during the Big Bang, which created all the matter and all the energy in the universe. So the energy that flows through you, yes, it ultimately comes from the sun, but it comes from the fusion of hydrogens, of basically protons, to form helium nuclei, which include both protons and neutrons. So these elements like carbon, nitrogen, hydrogen, oxygen that are made up of protons, neutrons, and electrons, those protons, neutrons, and the energy they store has been around for 13.7 or 13.8 billion years. That's how old those fundamental building blocks are of all matter. Now, we're life, right? We're made up of more than just protons, neutrons, and electrons. Actually, that's all we're made of. But those come together to form the elements: carbon, nitrogen, oxygen, calcium, right? Magnesium, iron, sulfur. Where did those elements come from? Well, here's a really cool thing. They came from stars. I know. So fusion doesn't just make helium and release energy like what our star is doing right now. Nuclear fusion inside of stars larger than ours also creates the heavier elements that make us up, like carbon, nitrogen, and oxygen. So through nuclear fusion inside of large stars, that's where these heavier elements came from. So most of the elements, or actually 90 of the 92 naturally occurring elements, were made inside of stars, sort of. Now, large stars, much bigger than our sun, at the end of their life, they blow up and they form these intense explosions called supernova. And a supernova explosion is so amazing that it will outshine a billion suns. And they're so powerful that they create all the elements larger than iron. So are you wearing any gold or silver maybe? Ever heard of lead or mercury, uranium? Those elements were actually made when a star blew up during a supernova explosion. Now, what does all of this mean? It means we're stardust. Isn't that amazing? We are literally stardust. Our entire rocky planet and every element in us except for hydrogen was made inside of a star that lived and died billions of years ago. So as you can see, we have these ingredients of life. The energy was created during the Big Bang. The fundamental building blocks, the subatomic particles of all the elements, they were made in the Big Bang. And then the inside of stars. So we are definitely dependent processes. So that to me is kind of really cool. Now, talking about biology, these elements come together as molecules, and those molecules are held together by chemical bonds. Things like where they share electrons, that's called a covalent bond. Or if they're like these ions that are oppositely attracted or oppositely charged, are attracted to each other, it forms ionic bonds, like in salt, like sodium chloride. But we form, for most of our elements, we form covalent bonds, or most of the elements needed for life, carbon, nitrogen, oxygen, hydrogen, they form covalent bonds to hold them together to form molecules. So we have in our bodies tens of thousands of different types of molecules made up mostly of carbon, nitrogen, oxygen, hydrogen, a little bit of sulfur and some other ones in there as well. And they're held together, like I said, by these chemical bonds. Now, here's what's interesting. Of all the elements in the universe, there's 92 of them, plus there's some heavier ones. They go to about 115, 116 that we've made in a laboratory, probably made inside of giant supernova explosion too. They just don't last but milliseconds. Let's see if I can adjust this light a little bit better there. Oh, well, that looks dark and scary. We'll be all right, though. At least I'm not getting blinded by my light. I know. It's hard to get the lighting right. But let me get back to this. We've got 92 naturally occurring elements in the universe. 4 of them is 96% of you, and that's hydrogen, carbon, nitrogen, oxygen. I know I keep saying these over and over and over again, but it's it's carbon. Carbon is the single most important element for life. And in fact, all the molecules of life, which we call organic molecules, are built around one element, carbon. And I've actually got a great video in there that says, why is carbon the element of life? Videos, other than a mockingbird singing, which is kind of cool. But that element carbon can form 4 different bonds, 4 covalent bonds. Covalent just means you're sharing electrons. And so carbon can form lots of different types of molecules, and they're all stable. So you'll learn about that. Like I said, you'll learn about how carbon can form, lots and lots of different molecules. So that's why organic chemistry, which is organic, having to do with life, is built around the element carbon. There is no other element in the universe this is versatile as carbon in terms of being able to form so many different types of molecules required for life. Now, any of you sci-fi fans out there, right here, love science fiction. They often talk about silicon-based life. Highly unlikely. And the reason why is silicon, even though it's just under carbon in the periodic table, it can form 4 covalent bonds. Those bonds are not stable, and they can't form the variety of molecules that carbon can. And that's important. And then next in this chapter, after you learn about, the ingredients of life in terms of where we came from, where the elements came from, how different types of bonds hold our molecules together, the importance of carbon for organic molecules, then the last part of the chapter is on water. And that's the last video. I'm trying to get that video done here as quickly as I can. The other ingredient you need for life, you need the building blocks of life, which are elements that form molecules. You need energy, and you need a median for all of these chemical reactions of life to occur. Because remember, life is an emergent property of a complex system, right? And that system is all these interacting parts within a boundary. That boundary might be a cell membrane for an individual cell, or it might be, the outside of our body. But the point is, life is at our most basic level. We're based on all these chemical reactions, right? So water creates a median for chemical reactions to occur. If it was in air, they'd be way too diffuse. If they were solid, the molecules would never come together. So it's water. So in the last part of this chapter, I talk about, what makes water such a unique molecule. It's polar. It's a polar molecule. It's got a plus and negative charge to it, or partial charges that allow it to stick to each other. It's a great solvent. It can dissolve anything that's hydrophilic. Hydro means water. Philic means loving. So hydrophilic is water loving. So you know this. You ever like taken sugar and put it in a drink, or you're drinking a soda and there's like tons of sugar in the soda? That's because sugar is hydrophilic; it dissolves in water. So because water can dissolve all of our ions like sugars or it can dissolve all of our ions like salts and a great many other something like sugars. Actually, this doesn't have sugar; it's got aspartame in it. For all these chemical reactions to take place, and that's needed in water, and why life after billion years of evolution, we still depend on evolved this independence of water, and it can't. You have to have water, and it's really interesting because I said last week, we're like in the golden age of exploration, of finding about our own solar system and finding exoplanets. And one of the things we look for life or the potential of life is a liquid water. And we found that potentially on Mars, definitely on moons of Jupiter and Saturn. Very exciting that we probe there and look for life on those different moons and on Mars. In fact, we have a rover is going to land on Mars in the next couple of weeks. Exciting times. I can't wait. And it's going to look for life, which is really cool. The other thing about water that you need to be aware of, why is it so important for life? Well, it's a good medium for all of our chemical reactions. It dissolves a lot of things, not a universal solvent. Not dissolves a lot of things, but it's not universal. And the other property of water that's very important is pH. I know I risk losing people immediately when you start talking a little bit about chemistry, but pH measures the acidity or the alkalinity of water. You see, water is a molecule, right? It's made up of hydrogen and oxygen, two hydrogens, one oxygen, and they're held together by these strong chemical bonds, right? But every now and then, some of the hydrogen pops off the oxygen. If you have an extra hydrogen, you have an ion, and then you have the OH, which is a hydroxyl group, which is also an ion. And these are reactive. So when you change the pH, you change how much of the hydrogen ions you have or how much of the hydroxide ions you have. So if you become more and more acidic, you increase the pH, which is the potential of hydrogens. You get more and more of these hydrogen ions, which is basically a proton. It becomes more reactive because those ions can interact with your molecules and cause chemical reactions to happen. Become increasingly basic. That can cause chemical reactions to happen. It can alter the chemistry of our cells, and it can alter the shape of our. We haven't gotten into proteins yet. That's in chapter 4, but it can definitely alter the shapes of those proteins and render them useless. So the chemistry of life is geared toward very specific pHs. And in fact, your blood has to be at a very narrow range of pH, slightly alkaline. If it becomes too acidic, it's called acidosis. If it becomes too alkaline, it's called alkalosis, and you can die rather quickly if your blood becomes too acidic or too basic. And it dies because, well, you can't unload your oxygen or pick up carbon dioxide and unload it as well. So your blood maintains very controlled pH. The cells of your muscles, very controlled pH. Your stomach, very low pH. But your intestines, like your small intestines, is alkaline. And like I said, all the enzymes, all the cells in there are adjusted toward very specific pHs. Now, that being said, don't worry about eating to your pH or anything like that. Your body has a very good ways of buffering your body. So you don't have to worry about whether or not you're eating acidic or alkaline food for your blood pH. It does not kind of affect it over time. Okay, and then lastly with pH, as I said, not just as our physiology, all the chemical reactions in our body, very in tune to very specific pHs. Other organisms are, and so are different ecosystems. So one of the problems with global climate change, and here we go on global climate change again, one of the biggest threats we face, right? But with this global climate change, we're releasing enormous amounts of carbon dioxide into the atmosphere. And a lot of that CO2, carbon dioxide just means two oxygens, gets into the ocean. And once it is absorbed into the ocean, like half of all we've released, it forms an acid, a weak acid, carbonic acid. And by forming that weak acid, it's lowering the pH of the oceans. So we're acidifying the oceans. And that's actually really bad for a lot of marine life. Think, how many of you like oysters? Oysters. They actually shut down the oysters where I'm at. I'm coming at you from Florida, and they shut down the Appalachian Bay where I grew up. One of the two biggest oystering areas in the country. They shut it down. Think about coral reef, calcium carbonate homes out of it, which is like a rock. It's like a limestone. And oceans become more and more acidic as the pH lowers. It gets harder and harder for these organisms to make their shells if you're a snail, or to make your shells if you're a bivalve like a scallop or an oyster or a mussel, or if you're a coral, you can't build your reefs. So this is a real big problem in our oceans. And to make it even worse, think about this. The coral reefs on our oceans account for like 1% of all the ocean surface, actually a little bit less. But nearly half of the ocean's diversity is on these coral reefs. So half of the ocean's diversity is in less than 1% of it. Those 1% is dependent on these animals, these tiny animals, to build these large reefs by taking calcium carbonate and making rock out of it in the ocean. If we acidify the oceans, we affect their ability to make these reefs, and we're going to greatly impact the diversity of the oceans. So as you can see, pH really, really does matter for both our physiology and for ecology and conservation as well. Well, I see that some of you have joined in. Thanks for the thumbs up. Always makes me happy to know that you guys are liking this. If you have any questions, feel free to ask. You know what? Never hesitate to ask a question about the course material, anything I'm talking about, or anything on science in general. It doesn't have to be limited to exactly what's happening that week. I'm happy to entertain any questions you guys have about science in general. This is your one time, like, here I am. Shoot, I'll either if I know the answer, I'll tell you, or I'll just speak with authority. Not just kidding. I'll let you know if I don't know the answer to it. There's so much out there that I don't know, and I'm always trying to learn. But I have been thinking about science and reading science and studying science for decades, and I love it. So if anybody has any questions, shoot. If not, I'm gonna sign off and go hang out. My dad recorded not the Colbert Show anymore. It's a late night show with Stephen Colbert, so we always watch that this time of night. Okay, anybody else? No questions? Hey, thanks for the thumbs up. I appreciate it. Next week, of course, we will have a test. No new material. I'll pop on live for a test review next week. Okay, well, you guys have a good week and stay safe out there. Good news. COVID cases are going down. People are getting vaccinated. Yay.